Hello, my name is Basil and I'm going to present the paper Multi-Agent Trajectory Prediction with Fuzzy Query Attention. Okay, so let's start with the problem description. So this paper suggests a general architecture for the task of trajectory prediction for all agents in the scene. And the input is a spatial coordinate PIT, which is the position for each agent, presented by X and Y. For all agents, I in the range of 1 to n, for a given duration ranging from 1 to t observation. And the output of this model is a spatial coordinate for the future. So we have a position, predicted position, x and y, for all agents I, in the same agents I, ranging from 1 to n, for the time t observation plus 1 till t prediction. So we are predicting the following positions. And the paper used several datasets, and they are ETH-UCY, the human crowd trajectories, and GSIM, which is US freeway traffic, NBA, which is port data, collision is a synthetic physics dataset, and finally charges, which is a physics dataset with positive and negative charges moving in electrical field due to other electrons moving. So the idea of using 5 datasets is that the author tried to highlight and show that their methodology works well across different domains. Next, we describe the model used in the paper. So it is divided into 3 diagrams. The first diagram shows an overview of the system. So we have the input, the position for each agent, and we have the first module here is the inertia module, which represents the constant speed of each object. And we have the intent module, which represents the intent of each agent, and the interaction module, which represents the resultant velocity change for each agent resulting from the interaction with other agents. So let's check the output or the future predicted trajectories for each agent is the addition of the position for each agent and the velocity, the constant velocity, which is the inertia, and the change in velocity resulting from the interaction module. This sum represents the future trajectory or positions for each agent. So now let's check each of these modules. For the inertia, it is the difference between the successive positions, so t minus 1, p of t of minus 1 for each agent is subtracted from each agent position, and this generates the velocity, constant velocity for each object or each agent. Then the position also is fed to the intent, which is captured using an LSTM module. The LSTM module hidden state is fed to the interaction module, which is then calculates the velocity change. So let's check the interaction module, which is explained here. It has as an input the position for each agent and the state for each agent. It first calculates the graph between the different vehicle or different nodes in the agents, and also so the input here is the graph, the position and state of each node in the graph. So the first thing is to calculate the sender and receiver feature, which are the sender and receiver are the nodes in the graph, the corresponding with a pair of nodes in the graph connected, and the feature here are the position and state for each of the sender and receiver, and also the relative position between the sender and receiver, similar for the state, the relative state, and also the unit vector of PSR and HSR. So these features are fed to fully connected to generate keys and values, keys and queries, which are using a dot product and added to a bias, a learned bias, generate an attention mechanism like. Actually, this is a variant of attention mechanism, and fed to a sigmoid function. The sigmoid has a range of 0 to 1, so the output here is a decision where the 0 represents no and 1 represents yes. This is an analogy from the author to map the output here to a fuzzy-like approach. So we need now to calculate the response or the value of for the yes and value for the no. So we use a fully connected layer using an input of PSR and HS, which are the state and position, relative position between the sender and receiver, and the state of the sender. We pass that through two fully connected layers to generate VOI and VN. Then VOI is multiplied by DSR and added to 1 minus DSR multiplied by VN. So the output here is concatenated and fed to a fully connected layer, which is then max pooled to aggregate all of the sender information, and then passed to a fully connected layer to calculate finally the attention of each receiver or each agent. The metric used is the RMSE between the ground truth and the model prediction, and the training is performed for 5 datasets and compared with 6 other baseline models. And to highlight the importance of each module in the model, an ablation test is performed with 5 variants of the model. The first variant is the modeling only, is to model only the inertia. Another one is to model only the inertia and the agent intention. Then we have removing the decision-making part of the FQA. And FQA proximity is about, in the generation of the graph, the nodes that are more than a distance of a specified distance, a threshold distance, are not connected in the graph. So this allows to investigate the FQA ability to model the distance part between the nodes and each other. And lastly, to involve the human knowledge as a fuzzy input or in the decision-making part. In the result, we can see that the model outperforms all the other 6 models on the different tasks or the different datasets. And for the ablation part, we can see that all of them, when we remove each component in the ablation test, for the inertia and no interaction or no decision making, they are all perform worse than the baseline or the FQA. And also for the distance based, we can see that when we involve this information, the FQA outperforms the other models in like 3 out of 5 distance, while still having comparable error to the best of them in the NBA and NG sim dataset. And when we involve or add the human knowledge, it doesn't show much of increase in the performance, but still it's still within it still doesn't decrease the accuracy or the error or increase the error. As an overall, the model is able to represent the interaction between the agents and incorporate the attention mechanism with the graph representation, and therefore overcome or improve upon the state-of-the-art models available. So to suggest an enhancement, it is better to focus on the intent of the agent, because in this approach, a simple LSTM is only used, but maybe using a hierarchical policy network instead of this LSTM would be much more efficient. Another suggestion is to split the interaction velocity, change, which is delta V, into 2 parts, V1 and V2. So one for the intent and the other one for interaction, so that both of these are independently added to the summation for with the position and inertia for the future path trajectory. The intuition is to allow the model to learn the intent and the interaction separately, therefore hopefully to better represent them. This is our reference use, and thank you.